So in this lecture we will derive theorem 2, which says that assuming a1 a2 till an be my mutually exclusive set of events, we can assign probability as p of union of 1 to n ai is equals to summation of probability p of ai from 1 to n. If we interpret this, we say that probability of union of all ai's ranging from 1 to n, like all individual probability a1 a2 up till an, all these union probability of all these unions will give me the summation of all individual probabilities. And if one will observe that this is quite distinct from the axiom 3 of the probability, which says that probability of union I is 1 to infinite a of I is equals to summation of I is equals to 1 to infinite probability of a of I. This is axiom 3 of the probability, and we need to now show that this expression for a finite countable additivity, it follows this rule. Okay, probability of all the unions of ai's will give me the summation of all individual p of ai's. So ideally we will be using this axiom 3 in our proof. So we'll see how it begins. So the proof, let us assume that out of using assume that out of this infinite set a1 till an, this is my finite set, and after that a n plus 1 a n plus 2 dot dot dot, this my infinite, it will continue. So assume that a of j, where j is ranging from n plus 1 n plus 2 dot dot dot, they all are null set. Only we have n number of finite set and rest all is my null set. Then we invoke axiom 3 to prove the above relation. So we'll see now. That's it. So using axiom 3, we can write probability of union of all the ai's is same as sorry, there is a mistake. No, let us proceed in that way as well. There was no mistake. Probability of union of all the ai's can be written as summation of p of ai I is equals to 1 to infinity. This summation can be broken down as a finite sum and infinites. I is equals to 1 to n, which is finite. Then from I ranging from n plus 1 till infinity, we can write p of ai. As per our consideration, we have assumed that mostly this p of ai is finite, null. By this assumption, we can say that just in the previous lecture we have seen p of phi is nothing but 0. Hence, we can write like this: summation of p of ai and I is equals to 1 to n. And here also, as we have considered a1 an as our finite and rest an plus 1 as phi, if we take I is equals to 1 to infinity a of I, it is same as union of y is equals to 1 to n ai. Hence, we can write probability of u is equals to 1 to infinity a of ai is same as probability of u of ai ranging from 1 to infinity. This is my equation 1. This is my equation 2. So based on equation 1 and 2, we can come to conclusion that P of union I is equals to 1 to n A of I is nothing but summation of all the P of AI ranging from P is equal to 1 to n. This is for finite additivity. Finite additivity. The previous was the countable additivity, this was the finite additivity. Now, heading on, we want to prove one more theorem, which says let me change the color. This will be theorem 3. For any event A, we can assign probability of A complement is nothing but 1 minus probability of A, assuming A and A complement are disjoint in the entire sample space S. What it means that consider this is your sample space and you have only two events, one is A, one is A complement. So when you take A intersection A complement, it is null, and when you take A union A complement, it is the entire sample space S. So by the axiom, we will use one of the axioms. So if we take probability of this set A union A complement, and on the right hand side we write P of S, we know P of S is 1, and by the rule of finite additivity, if we invoke finite additivity, we can write this as P of A plus P of A C, which is equal to 1, and from there we can say P of A C is 1 minus P of A. This was a short simple proof which says a very critical information about this theorem, that any complement of a set, probability assigned to any complement of the set is nothing but 1 minus P of A.